Okay, we're going to do some practice with the rational root theorem. I like to make a little table. So I'm going to take the factors of 6 and I'm going to put them right here. So the factors of 6 are 1, 2, 3, and 6. And we need to divide those by the factors of, the only thing here is 1. So for the possible factors for the rational root theorem, it's just 1 over 1, 2 over 1, 3 over 1, and 6 over 1. And then you account for the negative values. So you would get plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So those are all of the possible rational roots for this. Okay, we're going to do another one where we practice that. So again, up here, I'm going to put the factors of 2. And on the side here, I'll put the factors of 3. And so the factors of 2 are just the number, it's just the number 1 and 2. And then the factors of 3 are just 1 and 3. So to find all the possible factors, I just divide these in all the combinations, but I always divide the factors of the constant by the factors of the leading coefficient. It's never the other way around. So I'm going to divide, 1 by 1 and 2 by 1. And I'm going to divide the factor 2, this other factor of 2, which is 1 by 3, but I'm not going to divide 3 by 1. 3 is not going to be a possible rational root of this polynomial. Same thing, I'm going to divide 2 by 3. 2 over 3 is a factor, but 3 over 2 is not a factor. So it's always factors of the caboose over factors of the locomotive, or factors of the last term over the factors of the leading coefficient of the first term. And then you also take care of the plus or minus cases. So if you want to list all the possible factors out, you would get all those values with just like a plus or minus in front of them. Notice there are no duplicates. If there was a duplicate, like say if some other term was equal to 2/3, like say there was a 4 over 6, I wouldn't count that twice because I wouldn't want to write it out twice once we're simplifying. But in these, there are no duplicates. All right, so the next one, we're going to take the factors of 12 and divide it by the factors of 4. So I'm going to set up my... So I like to list the factors of 12 on the top to remember that I'm dividing that. I'm always using that as the numerator. And these are not on top, they're on the side, but that reminds me that it's the denominator. So I just write down the quotients right here. And, the 2 over 1, I'm going to eventually simplify to 2, and the 3 over 1 I'm going to simplify to 3, and 4 over 1 will simplify to 4. But I just like to, even though I know when you divide by 1, you just get that number, I just don't want to forget that I'm always dividing. So this is just me showing my work right here. And then across this row, we divide 1, the red 1, by the green 2. Divide 2 by 2, 3 by 2, and you keep doing that all the way. And just to really be clear so that you can see at a glance what's going on, I wrote this in this last row, I wrote these in red, and then the 4s I wrote in green, so you can see I'm dividing, the red 1 by the green 4. Now, before I write out the factors, I don't want to count the duplicates. So yeah, 1, 2, 3, 4, 5, 6, 12. But notice how 2 over 2, that's the same thing as 1, so I'm gonna cancel that out. Also 4 over 4, that's the same thing as 1. Basically anything that can be reduced, once you reduce it, you might see that it existed somewhere else in there. Another one, 2 over 4. 2 over 4 is the same thing as 1 over 2, so I don't want to write that as a separate, distinct possible root. 6 over 4 is 3 over 2, and hey, look, that pops up there. 12 over 4, that simplifies to 3. 12 over 2, that simplifies to 6, which pops up here. 6 over 2 simplifies to 3, so cross that out. 4 over 2 simplifies to 2. So there's a lot of repeats in here. So all of the first row, that's going to be our possible roots. These ones that are left over in the second row, and then these two that are left over in the third row. And I'm going to write all those out as the possible roots with plus or minuses. So when I list all those out, this is the complete list of the possible rational roots of these. Now, remember, I just want you to be able to organize. This is really just a strategy and organization. You can test these roots when you want to find if they are the zeros, but we're going to use, I tend to favor graphical methods or, just other methods when you're trying to find the zeros, but this is really just kind of a practice in organization. But these are all the possible rational roots, all the possible roots that are rational numbers. Okay, we're going to do the same thing for this one. This one will be a lot easier. If you look back at 42, notice how the reason there were so many, it was so big and there are so many duplicates because 12 and 4 are not prime, whereas in a lot of the previous examples, like 2 and 3 are prime. And the first one, 6 isn't prime, but the 1 is. So it really eliminates the possibilities because it eliminates like the combinations you have. Like 12 has 6 factors and 4 has 3 factors, and so there's 18 possibilities, and they do get kind of narrowed down. But when you have numbers that have a lot of factors, it makes a lot of possibilities. But with prime numbers, well, there's only 2 factors for 7, 1 and 7, and there's only 2 factors for 3, and that's 1 and 3. So altogether, there's only going to be 4 possible rational roots there. 1 over 1, 7 over 1, 1 over 3, 1 over 7, and then you just do the plus or minus case. And so you get these 4 possibilities, and here there are no duplicates. And that's it for the rational root theorem. Those are all the practice questions that you're going to have for those. Next up is 48. So we're told that a polynomial has rational coefficients. That means that we get to apply some theorems there. That we know that if it has any imaginary roots, or really I should say complex roots, because this part is real and only this part is imaginary. Anytime you have a complex root, it has to occur in pairs. So we're going to name those additional roots. So since 1 minus I is a root, that means its conjugate, which is 1 plus I, also has to be a root. So we know that this is another root. Now, with real roots, they don't necessarily occur in pairs. So just because 5 is a root doesn't mean negative 5 is going to be a root. It only works with irrational roots, which are usually like square roots, and complex roots. That's when you know the conjugate exists. So that is one of the root you know has to exist for number 48. Okay, similarly, if you look at 49, we know that if a polynomial has rational coefficients, anytime there's complex, which is like what we had in 48, or here irrational roots, we know they have to occur in pairs, so we need to include the conjugate of this irrational root, which would be 5 minus square root of 3. So we know that's going to be an additional root. And we also know that, well, negative square root of 2, well, really that's negative square root of 2 is really 0 minus square root of 2. Oh, so that means that positive square root of 2 would be the conjugate of that. So we know that these two other numbers would also be roots of that polynomial. For number 50, again, this thing it's a polynomial with rational coefficients. So this is complex, and this is actually technically purely imaginary. So since it has an imaginary root at 0 minus 3i, we know that 0 plus 3i, or I could just say 3i. I don't need to write the plus. The positive is understood. That has to be root, and then the conjugate of the 7i, that would be negative 7i, or 0 minus 7i. So those would also have to be roots. Again, this is from the complex conjugate root theorem, or simply the conjugate root theorem. So it's just the conjugate root theorem, which applies to complex numbers, but also irrational. So you have to have those conjugates pop up. Last one, where we're focusing on the conjugate root theorem. So if negative 2 plus square root of 11, that's irrational. That means that negative 2 minus square root of 11 would also have to be a root. That's its conjugate. I didn't negate the negative 2. You only negate either the irrational or, in this case, you negate the imaginary part. You never negate the real or rational part of that. So both these conjugates have to be roots if their imaginary or irrational original forms are going to be roots. All right, next problem, I'm asking you to find the number of roots for the equation. Now, you can go through a bunch of work and actually find the exact roots, but I just want you to first, we'll do that later, just find the number of roots. Well, if you include this says the total number of roots, so that includes real roots, that includes complex roots, And that includes, for real or complex, when you have any multiplicities. So it's like if you have a root that occurs more than once. Either way, we know that according to the fundamental theorem of algebra, you should know the number of roots is just equal to the highest degree of the polynomial. So this thing is going to have 3 roots. And that's all I want you to know, is that whatever the highest degree is, that's how many total roots, which could be any combination of real with multiplicities or complex involved. Just look at the highest degree. For the next one, well, let's see. Well, this doesn't seem to have a degree. Oh, wait, it's not written in descending order, so the degree here is 4, so this one's going to have 4 roots. You always look for the highest degree. For number 62, again, just look at the highest degree in there. So this one's going to have 5 total roots. And finally, number 63. Well, let's see. I see a 4th power here. So initially, I'm thinking, all right, maybe this will have 4 roots. But that would be wrong. And can you see why it's wrong? Well, again, it's not written in descending order, so it's really cruel of them to not write it in descending order. So make sure it's written in descending order first, or just look for the highest power. That's why it's important. That's why we have these, these forms that we write polynomials in. So this is actually going to have 6 roots because it's a 6-degree polynomial. Okay, for 64 and for the next few, I want you to actually find the zeros. Now, I'm going to do it 2 ways. First, if you like the rational root theorem, I know that the most likely roots are going to be 2 over 1, since that's the factors of 2, 2 over 1, negative 2 over 1, and then positive 1 over 1, and then negative 1 over 1. So those I can check using, I'm guessing those using the rational root theorem. Now, you could take those and you can individually test each of those roots using synthetic division. So let me, and this is the slow way of going through it. If I use synthetic division, there's 1, 5, negative 4, negative 2. I want to see if 1 is a root, okay? So drop this 1 down, multiply 1 by 1, that's 1. 5 plus 1 is 6. 1 times 6, and then that's negative 2. And then 1 times negative 2 is negative 2. And so, oh, actually, I messed up here. So, actually, negative 4 plus 6 is a positive 2. And 1 times 2 is 2. Hey, look, we get a remainder of 0. Now, what that means is that 1 is a root, so that means that if I list out my zeros, one of my zeros is the 0 that is x equal 1. And if you're looking at the linear factor version of that, if you factor it out, you'd be factoring out x minus 1. But what's interesting is that now, since I divided by that polynomial, I get x squared plus 6x plus 2. And I can test to see, hey, maybe there's some other of these numbers that are, that are zeros. But instead of doing that, I already have a quadratic. Let's use quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to plug that into quadratic formula. That will be negative. In this case, my b is 6. That's plus or minus the square root of b squared would be 36. All right, minus 4. The a is 1. The c is going to be 2. And that's going to be all over 2 times the a being 1 here. And then I'm going to try to simplify this if I can. So 36 minus, that's 8. So 36 minus 8, which comes out to 28. So this is negative 6 plus or minus the square root of 28 all over 2. And let's see if this radical can be simplified. So again, this is a lot of work here. Negative 6, the I know that 28 is 4 times 7, so that's really square root of 4 times square root of 7. So this is -6 plus or minus square root of 4 is 2, so that's 2 square root of 7, and all this is over 2. And then all of these are reducible by 2, so this comes out to, if I divide this by 2, it's -3 plus or minus. These 2's cancel out, so that's just square root of 7, and then that's all over 2. Now that's one way you can do it. You can also use your program on your calculator. Once you have a quadratic and you go to Program and you go to Quadratic Formula, and you can just enter, the A, the B, the C, and it also, if you want to do it by hand, you can write it that way. But here is these same values should be the same values we got by hand, and I'll just try to convince you that they are. So we got -0.35 and -5.6, and those are given as decimals. But I mean, it still gives you the answers. And if you ever run into a multiple choice part of the test, and it's like the answers are only in this radical form, well, you can just sort of kind of match them up. So we know that these are the right answers. So if this is one of the choices, let's take, I'm going to do alpha y equals just to make it a nice stacked fraction. So I'm going to type -3 plus the square root of 7. So -3 plus the square root of 7, all of that over 2. And if you notice, I get that value right there. And when I check the answers, oh, terrible news. That means when I did it by hand, I clearly did some calculation completely wrong. So that's kind of why I prefer using the program anyway. Even the math teacher goofs up on the calculations. Now you can also find these zeros graphically by doing second calc, and you do the 0. And I can confirm that when I did it, and when I do it this way, yeah, I get the same thing I got when I use quadratic formula, which can be seen right here. And I can find this 0 as well. Second calc, go to the 0, and the one way on the left should be the -5.6 roughly. So left bound, right bound. So there it is right there. And all of that is, this is all from the original function. So I know that doing it the quadratic formula way got me the right answer. So what happened was I actually just, here I just reduced the one. You can see the original thing works out just fine, but my reduced form right here, you can see it right here. Putting the reduced form, I did a little bit off. And I'm just realizing that when I canceled out the 2, yeah, I carried the 2 over. So if you want to put it in radical form, it's -3 plus or minus the square root of 7. But in decimal form, what you get from using the calculator, it's just these decimals right here. So these are your 3 roots. Your zeros, one of them is x is equal to 1. So for your zeros, x equal to 1, and then x equal to approximately -0.35, two decimal places, and x equal to -5.65 if you round up to 2 decimal places. I'll be fine with the decimal approximations. If you want to put it in exact form, you're welcome to, but I really just encourage you use the decimal approximations, because when we use these practically, like when you're solving for zeros in practical situations, most of the time, the x value is like time. Like it's like the x value, x-axis is the time axis, and it just makes more sense to put it in values we understand. This value, like I can't approximate this at all or understand what this number is without using a calculator anyway. So please feel free, if you don't want to use the quadratic formula by hand, just use the one on your calculator, or if you could use the quadratic formula, at least enter the value. Feel free to enter the value as is into your calculator. And even if the answers happen to be imaginary, which some of them might come out there, make sure you have it in that complex mode so that it'll account for those numbers. All right, that's it for that one. But actually, before we move on, like I told you, you can use the rational root theorem to start this off. But if you'd like to avoid the rational root theorem altogether, all of the ones on the test, I will give you at least one zero that is real. On this one, if you plug this into your calculator, all of them just so happen to be real. But if you want to avoid using the rational root theorem, you can just find at least the real zero graphically by using second calc 0. So there's one of the real ones right there. Like it happens to be 1, which we found. I got lucky on my first guess and used synthetic division. It happened to be that x equals 1 was a 0. But if you just do it graphically, you don't have to guess. So please use the graphing function on your graphing calculator to find one of those real zeros. And once you find out whichever the real one is, you can use synthetic division and get this down to a quadratic equation, and then use quadratic equation to find the remaining 2, or you can just stay using your calculator and using that second calc 0 option if the other 2 zeros are in fact real as well. Okay, moving on to number 65. Now only the honors will have a fourth degree polynomial that they have to find the zeros for. And again, you can use rational root theorem. If you look at the factors of 20, 1, 2, 4, 5, and 20. And the factors of this are just 1. So the only possible roots are positive or negative 1, 2, 4, 5, and 20. So those are already the zeros that I'm expecting. So you can use rational root theorem, but to find at least some of the real zeros, please feel free to, again, use your calculator. So go into your y equals. Instead of using rational root theorem, just go x to the fourth power, all right, minus 4x to the third. Put that rest of that polynomial. Once you have it in there, just go look at the graph. And usually when you're looking at the graph, I recommend when you take your first look, maybe look in the standard window, and that's zoom 6, which I'm already there. But here I can see at least 2 zeros, it looks like. So there are definitely 2 real zeros for sure in this fourth degree polynomial. Now I can find out what those are. I can use my calculator, do second calc, go to 0, and I'm going to find this one on the right here. It seems to be just 1, but there it is around, like, it's about 2.23, so that's one of the zeros. And I can see the other one. This one looks like it's really close to -2, but I'll do second calc 0 just to be sure. And I'll do that one that's on the left of the y-axis there. So it hops really quick. So left bound there, right bound there, and that one comes out to that same number, but it's just a negative. So that's pretty much seems like to be like the conjugate of an irrational number there. So it's the negative version of that. That's the other one. Now let's take a closer look at, because it seems like there's either another 0 here, or this, for some reason, the graph is getting it's really hugging this part of the curve, this part of the x-axis. Can you remember what causes a polynomial to kind of flatten out and hug an x-axis like it appears to be doing here? First, let's zoom in on that point. And we're zooming in on that point that's around that positive root there. And when we zoom in, it seems to be flattening out. So that usually means for it to flatten out, the only time it does that is when you have a high multiplicity. So this thing actually has only 2 zeros, one of them being the negative 2.23, and this one positive 2.23 or 2.24 if you round up to it. But the positive 0 obviously has a high multiplicity. So, and for it to have a high multiplicity, but it doesn't bounce off the x-axis like this, so the multiplicity must still be odd. So since it has an odd multiplicity, that must mean that it's not 1, it has to be 3. Well, if this has a multiplicity of 3 and this one has a multiplicity of 1, that accounts for all 4 of the zeros we expect. So that's all of our zeros. So the zeros of this are negative 2.24, I'm just going to round to the nearest hundredth, and positive 2.24, but this one has a multiplicity of 3. And again, that's because it hugs the x-axis right around. So this is our final answer right here. All right, next we'll look at 66. Again, I can use rational root theorem, and the factors of 2 are just 1 and 2, and that applies for both. So your possible factors are 1 over 1, 2 over 1, 1 over 2, and 2 over 2, but that's a duplicate, and I can check those, and I can check the positive and negative version of these using synthetic division until I get a hit. And let me show you another thing without synthetic division. So, because that's kind of cumbersome. Let's do this. I know the possible zeros are 1, positive or negative 2, and positive or negative 1/2. Well, let's try to find those zeros another way. So let's go to y equals. Let's put this cubic equation in. So we're putting this into I'm putting that into the y1 there. Oops, mistyped that. Now, without looking at the graph, I want to check if these are zeros, because looking at the graph, it's sort of ambiguous. You have to zoom in kind of well. Let's go to our second table set. And I like to have my table set. It doesn't matter what the table start is. It doesn't matter what the delta table is. Set the independent to ask. Set the dependent to auto. And that way we can custom enter our own x values. And then we're going to go to second table. So right here, I'm going to test. I'm going to clear out all these x values I don't care about. I want to see if this has a 0 at -1. It does not. So I could have used synthetic division to test it, but using a table on a calculator is a lot faster. Let's test it at +1. Yep, that is a 0. Now there have to be 2 others. So one of those others could be they could both be imaginary, they could both be real, but let's test these values. Let's see if -2 is a 0. It is not. How about +2? It is not. How about -1/2? I'm just going to enter 0.5. It is not. And let's check positive. Oops, I checked +5. Let's try 0.5. All right, it is not. It's close. So here's the thing. In this scenario, the real 0 is only the 1, the +1. Now, you could have also gone to the graph to see that. I'm going to go back to, and I happen to be in this nice zoom where you can see it. See how it hits it exactly at 1? Or go to zoom standard. And you can see that the only place where this cubic hits the x-axis is right there at +1. And to confirm it, you can do second calc. 0, left bound, just go left of the 0. It doesn't matter how far left you go. Go right of the 0. This is far right enough, but you can go further. There's nothing wrong with that. And you can confirm that the 0 is at 1. Well, the problem is there's only one real 0. The other 2 are imaginary, so we know that there's one real 0 at 1. So I'm going to show that I found that graph. And to find the other zeros, assuming that you already know that one of the zeros is at 1, well, to find the imaginary or the complex zeros, we can use synthetic division to divide out this 0. And then the quadratic that we get, because that's what happens when you reduce a cubic by 1 power, when you divide out a linear factor from a cubic, you'll get a quadratic. Use synthetic division here. 1 times 2 is 2. Add these, -1. -1 times 1 is -1. Add these, you get +2. +1 times 2 is 2. You get a remainder of 0. So this 2, and remember, this 2 represented this 2 represented an x cubed. This was an x squared. This was an x, and this was a constant. But it drops by a power. So this one is now an x squared. This was an x. This is a constant, and the number that's last is always the remainder. So what we have here is 2x squared minus 1x plus 2. You don't have to write the 1. I just like to write it. To find the imaginary, the complex roots, The only way we can do that is with the quadratic formula. So you could do negative, since b is -1, you do that plus or minus the square root of the b squared. I'm just going to write 1. Yes, I know it's -1 squared, but -1 squared is a positive 1 anyway. Minus 4 times 2 times the c is also 2, all over 2 times, this time the a is 2. And this is your answer right here, and you can reduce that radical. If we want to reduce that, you get, this is a positive 1, and I'm going to simplify this little determinant here. 4 times 2 is 8, 8 times 2 is 16. So a 1 minus a 16 is a -15, so it's plus or minus the square root of -15, and then that's all over 4. If I want to write that, there's nothing really wrong with writing square root of -15, but it's not a real thing. So anytime you're going to have a negative square root, you always want to convert it into and show that you know it's an imaginary number. So instead of writing square root of -15, we write 1 plus or minus I times the square root of positive 15 all over 4. And the 4 doesn't cancel out with anything here, so you notice I'm not reducing or anything. So here are your zeros. Your zeros are your roots. You can call them whatever you want. Your zeros or your roots are at x equal 1 and x equal to this these two values right here. And there are two values because one of them is 1 plus I squared of 15 over 4. The other one is 1 minus I squared of 15 over 4. If you want to do it on your calculator, I can just confirm that, like, you can do the decimal version right here. I times square root of 15, that's over 4. Oops, it does not. It's math. Oh, if you have a newer calculator, you'll have no problem doing it like this. If you have like the ones with the LCD. I didn't update my operating system, so it gets mad when I put i's inside of like an alpha y equals. So I have to enter it in this way. So I get 0.25, which is the 1/4. 0.25 plus about 0.9 something I. And if you do the minus version, just go here and put a subtraction sign. It's 0.25 minus, that same thing. Notice how it's a complex conjugate. And if you want to separate the real parts, so if you want to write it this way too, you can write 1, and then it's 1/4. If you want to write like 1 over 4 here, plus I on the square root of 15 over 4, and then 1/4 minus I squared of 15 all over 4. Those are your real roots. Or you can use your calculator to do quadratic formula. So you can go to your program, go to quad form, and then you can just enter those coefficients of that quadratic we got after dividing out that linear factor. And notice how we get the same thing we got from just doing the quadratic formula manually. So program's really nice. Keeps it very nice and organized like that. And just make sure that you round it to at least, if you're gonna round, you round it to at least the nearest 2 decimal places. I'll always specify in the test what I want you to round to. But if you ever are in some place where they insist that you put in radical form, this is how to do it. Okay, this will be the last one on this part of the video. Again, this will be only honors. We'll have to find a 4th degree polynomial. Again, if you want to use rational root theorem, you could take the factors of 18, which are 1, 2, 3, 6, 9, and 18. And the factors of this coefficient is easy, just 1. So all your possible factors you'd have to check are positive or negative, all these numbers right here. And I can use synthetic division to do it, but instead of using synthetic division, I'd rather just use the table function in my calculator. So I'm going to put this polynomial. Okay, once I have that polynomial in here, and just check to make sure you put all your coefficients, you put all the right signs on there. You could either graph it, or if you're really insistent on applying rational root theorem, you can go into your calculator and you can test each of those roots. So I have these in from a previous one, positive and -1, positive and -2. That just happens to be the same ones that were useful before. I can check -3. Oh, hey, -3 is a 0. Nice. So we're gonna have 1 0 at all. I'm checking plus or minus. So +3 is gonna be a 0. So I'm gonna keep that. Sorry, -3. Hey, -3 is gonna be the 0. So I can also check +3. That's a nope. And then I can check negative and +6. Hey, +6 is a 0, so 6 is going to be another 0. And let's go up here. Let's check -6. Nope. Let's check -9 and +9. Nope, nope. And let's check -18 and +18. All kinds of nope. Wow, those are so off. But if you want to avoid rational root theorem altogether, again, just go to Zoom, go to option 6. Let's just look at the graph. Just take a little gander at the graph. Hey, look at that. I can see that there are some zeros at this one. See, the -3 0 is right there, obviously. The +6 0 is there, but wait a second. Why didn't these pop up when I was finding the zeros when these were all my possible rational zeros? Well, they're obviously real, but that must mean that they're irrational. Now, if you want to find them graphically, you can look at the 0 here, and we can use second calc 0. Notice how it gives you a really weird decimal, like this 1.61, blah, 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 blah. If you want to find them as a decimal, yeah, that works great. And you can find the other one, again, using second calc 0. We can find the other 0 there. Just, go left a bit and hit enter, right bound it, hit enter. And this is going to be the other 0, which seems to be irrational. So you can find all the roots, real and irrational, using your calculator that way. Or, say you're strictly, you wanted to do it by hand, there is a way to do it. So we found, using the rational root theorem, you could find, the ones that are rational. And to get the ones that are left over, you could use synthetic division. So we could write this thing out right here, the 1, -4, -16, +21, oops, and +18. And you can divide out these factors one at a time. So let's divide out the -3. It really doesn't matter what order you divide them out. So divide out the -3, drop this, multiply, get -3. Add those, multiply, you get +21. Add those, you get a +5. Multiply, you get -15. Add those, you get a 6. Multiply, you get a -18. Of course, we get a remainder of 0 because we checked earlier using the table to figure out that those were the zeros. Now you have this thing that's like basically a 1x cubed, and then the rest of it is in descending order. -7, 5, 6. Well, now let's divide out the other known 0, which is 6. So drop the 1, multiply 6, and then add that. You get -1, actually. Then you multiply here, you get -6. Add that, get -1. Multiply, you get -6, remainder of 0. So this becomes 1x squared minus 1x minus 1. Then you take this thing and, well, how do we get these numbers right here from that? Well, you just run those into, you guessed it, quadratic formula. You could just do the quadratic formula by hand, but you've seen me do that enough times. I've had enough practice with it. I don't feel that I need any more practice. So I'm going to go to my program, quadratic formula, and just put in the coefficients. Hope I don't sound too arrogant saying that I've had enough practice. I'm a pro at this. But notice how the values we get using quadratic formula, since they're still real answers, they're irrational. So you can find them using quadratic formula. You could also find them graphically. Now, when they're imaginary, when they're complex, you have to use quadratic formula. But when they are still real, if like you have a fourth power function, all of them are real, you can find them all from the graph. All right. Again, this is fourth power function is one that will be honors only, so you do not have to attempt this question if you're not in the honors section, but that's how to do it. So that's the end of this first part of the video.